part, next week will be week 7, right?
Yes.
Okay, so I'll try to schedule your midterm exam. Okay, maybe on week 7 or maybe on week 8. Okay, because you have 2 exams with me. One is the DB and one is the cell tissue culture, right? So I'm trying to figure out how I am going to schedule this. I hope I don't put 2 exams in 1 week. Okay, because probably you have other exam on week 7 as well. Right. So today we're going to talk about the standard tissue culture and techniques. Yeah.
Recording in progress.
So what is standard culture techniques? So what are the techniques that is involved in this standard culture techniques? And basically, this standard culture technique involve subculturing, the quantitation, plating efficiency, cloning, freezing, and thawing. And of course, we will discuss how to select cell line or cell line selections, and also the characterizations of the cell line. Okay, this also will be discussed in this LU, right? So basically, what is subculturing? Subculturing basically is referred to passaging or splitting cells required periodically to provide fresh nutrients growing space for continuously growing cell line. We got to know that, yeah, when you culture the cell will keep dividing and they will use up the nutrients. At the same time, when they become more and more, the space will be limited. So when the space is limited, the nutrients is exhausted, then you need to do subculturing by providing fresh nutrients or fresh media so that you have the cell have more nutrients to continue to replicate and also the space for them to grow. Right? That basically that is the purpose of subculturing. So the frequency of subculture splitting ratio or the density of the cell treated will very much depend on the characteristic of each cell being carried. Okay, if you have fast growing cell, then the frequency of the subculturing will be much higher compared to the slow growing cell, because when you culture the fast growing cell, then this cell will divide very rapidly, and of course they will use up the medium in a much faster way, and at the same time they will use up the space as well. Okay, and different subculture strategies can select different properties in the cell line carried. So for example, when you culture the adhesion cell, what you need basically is a growth media. Okay, the phosphate buffer cell line, the PBS. Okay, they may be calcium ions or magnesium ion free. And this is the role of the PBS is like a buffer solution. Okay, or with the washing solution, and you probably need trypsin solutions in 0.04% of wet overweight for the tissue culture grade trypsin, and maybe 0.53 millimolar of EDTA, unless otherwise stated. This is the concentration that are normally used, and you probably need a culture disc, which is approximately 100 ml in size, and also the HEMA cytometer or electric particle counter for you to count your cell. So basically, this is the material that you need for the subculturing of the adhesion cell. Okay. So procedure is you remove the media from the plate. Okay, because you culture the cell is on the plate, and after that you wash it with one time with 5 ml of the PBAS, which is part of the phosphate buffer cell line, or this is what we call the digoxin, and add it with 3 ml of trypsin. Okay, and allow the trypsin to cover the plates, tilt the plates, and remove excess trypsin. Okay, the function of the trypsin here is to help you to digest a bit of the protein, so that because the cell, they are actually probably will attach together. So the function of the trypsin is to isolate them into the individual cell. Okay, and then you incubate at 37 degrees Celsius. And when the cell have rounded up, usually when you culture the adhesion cell, the cell is flattened. So when you put trypsin, then the cell become isolated and become an individual cell. And slowly when you incubate them, they become rounded up. and then coming off of the plate, and then you resuspend them in 5 ml of the serum containing medium, and also wash the cell by centrifugation them at 800 RPM, which is a rotation per minute, and after that we resuspend them in 5 ml of the medium. Okay, this is a very basic method for the subculturing of the adhesion cell. Okay, and if the cell are primary or secondary culture, or the cell lines is one of which you have had no experience with, a high seeding density is recommended. If you have no idea, yeah, no idea or no idea of the characteristics of the cell, then probably you have to reseed them in the higher density so that the cell can grow. Okay, the chances for the cell to grow is higher rather than low seeding density. And if you just now is the execution culture. Now, if you are subculturing the suspension culture, okay, you should know by now what is suspension culture and what is the adhesion culture. Can you differentiate them now?
Yes, doctor.
Okay, good. So culture of the cell that
Yes,
grow,
doctor.
okay, culture of the cell that grow in suspension in flux or the spinel can be maintained by diluting and all part of the suspension into the fresh growth mediums. So what are the materials that it needs? Probably is the flux. Okay, so depending on the volumes, you may use 75 centimeter flux and the growth mediums, and also the hemacytometer or the electric particle counter for you to count the cell. Okay, so the procedure is hold the flux upright and pipette the cell suspension up and down or 2 or 3 times to disperse any clumps. Because in suspension culture, the culture sometimes tends to be clumps together. So when you want to take the sample or what you want to subculture the culture, so what you need is you probably need to pipette them up and down for 2 or 3 times to disperse the clump. And after that, you remove an aliquot of the counting or the precise counts are not required. So you just transfer approximately 200 microliter to 1 milliliter of the suspension to a fresh flux containing 10 microliters of the growth medium, and then you keep on subculturing them. Okay. And this is the example of how the cell look like after 24 hours of subculture, for example, the NRK cell. All right. All right. The NRK cell, this is 24 hours after subculture. But after 3 days later, after 3 days of subculture, you can see the cell are dividing now. That the cell is in the log phase now. They are very much dividing, and they use up the medium quite easily. Okay, and if you look at this panel, then you can see that after 7 days of subculture, the cells are no more space for them to grow because they are too crowded, and also the medium already exhausted. So what you need to do now is to do the subculture, right? Because you want to provide more, you want to provide the fresh medium and also more space for the stem to continue to survive or continue to grow. So far, okay? Can you follow me?
Yes, doctor.
Okay.
Yes, doctor.
Good. So this is a serial subculture patterns or profile. You can see this is the exit of cell count of cell density, and this is the exit of the time. So if you see that if you start at 0, whereby you are receiving the cell, for the first 24 hours, you can see the cells are not growing at all because they are adapting to their environment. Okay, there are no growth at this, what we call the lag phase. Okay, the lag phase, no growing. But after they adapt to the environment, they'll start growing, and they are in the exponential way. Okay, until one time point, that's the cell no longer dividing. Okay, because they use up the nutrient, they use up the space, and you should know that by this time point, you should do subculture. Yeah. If you do not provide subculture, you do not subculture them, what will happen to the cell is the cell will reach plateau stage or stationary stage and lead to the dead stage. if you don't do subculture. So from what you see is the serial subculture here, you know that for every 7 days, you need to do subculturing. So the subculture intervals here is 7 days. So you can see at day 7, day 14, day 21, day 28 is the time whereby you need to do the subculture. Is that clear?
Yes, doctor.
Okay, so this is a subculture of the monolayer cell, okay, or the cell in the adherent cell. You can see that, okay. When the cell reach confluence, confluence means there are no space for them to grow. They are used up the space, and also the medium is exhausted. What you need to do now is to remove the media and wash with PBS. Yeah, and after you wash with PBS, you add trypsin just to cover them, so that they will digest the cell which they are touching each other, so that the cell later to become an individual cell. They are no longer touching each other, and then you remove the trypsin and leave the residue of the flames, and then what you need to do, you incubate the cell until the cell rounded up. Then become, these cells are flattened, now they become rounder. This is now like an individual cell, right? Can you see the difference here?
Yes, doctor.
Yes.
Okay. Now, what you need to do now after the cell is rounded up is so you resuspend them in a fresh media. And after you suspend them, you can do cell counting. You want to see the density of the cell, and also you can take the sample of this for reseeding. And then you reseed, maybe you take some of the cell, you reseed them in a fresh medium, and then after you reseed them, you let them grow. And after a few hours later, you can see the cell flatten again, because this is the adhesion cell. They need a matrix for them to attach to. Then you grow them. When they reach confluence, then you subculture them. Okay. All right. Can you see the figures on subculturing of the monolayer cell?
Yes,
Yes,
doctor.
doctor.
Okay, very easy, isn't it? So what subculture involved? First, they remove the growth media first. You remove the growth media, and then you wash with the plates with the PBSA, the phosphorus basal cell lines, and then you disassociate the adhesion cell by using the enzyme. Usually the enzyme is what you call the trypsin. Or sometimes you may use mechanical, like pipetting or gentry of scrapping. Usually pipetting is for suspension culture, but trypsin usually is for adhesion culture. Okay. So what are the criteria that we look for subculture? First, we want to look at the density of the culture, because you will examine the culture periodically. Yeah, you want to check whether the cell are reaching confluence or not. You want to see whether the cells, okay, use up the space or not. You usually will examine under the microscope. When the cells are reaching confluence, then you know that it's a time for subculture. Second, looking at the exhaustions of the media. When the media is exhausted, then the pH may change. Okay, the pH become acidic. So usually the phenol rate will change the color to become orangey, the orange color. So by looking at the color change of the media, you know that the medium is exhausted, and also there's a time for doing subculture. The third one is time since last subculture. For instance, you know that your cell, the subculture interval is 7 days. So if you count, if you look at the cell, if the subculture interval is 7 days, so you know on day 7 you need to subculture them, and on day 14, that's also the time for you to do subculture again, right?
Yeah.
Yeah. For example, if you know that the cell subculture interval is on the is 7 days, so you already know when is the last subculture. You know the last subculture is day 7, so you also know when is your next subculture, isn't it?
Yeah.
Yeah.
Yes, doctor.
So day 7, then the following subculture should be on the day 14. Then the next one should be
21.
21, then 28, and so forth, right?
Yeah.
Yeah.
So you should know this. This is the character of the cell, right? You should have the data ready with you. And also the requirement for other procedure. For instance, you subculture this cell and suddenly you say, oh, I want to test certain parameters of the cell. Maybe your supervisor asks you to test, for instance, the toxicity experiment. Or maybe your supervisor asks you to test for the nutrients requirement of the cell. So what you need to do, you need to subculture the cell again so that you have the fresh batch of the cell for you to do the new experiment or other for other procedures. Yeah? Boleh?
Boleh.
Okay, boleh ya?
Yeah.
Jelas, okay, good. So now the quantifications is very important too, because we want to know what are the quantity of the cell. You don't have to be accurate, but somehow roughly you know. Okay, for instance, how to quantify the cell? You can count the cell by using the Hammer cytometer or the electric counting or electron particle counter, or you may use a graph curve. Usually in the good lab, we use electric counting or electronic particle counter. And sometimes for the teaching purposes, then we use cell counting by using the Hammer cytometer and also graph curve. Okay, for teaching purposes, for experimental, for research purposes, for master level and above, maybe we use the electronic counting or electronic counter. Okay, so cell counting by Hammer cytometers actually is quite straightforward. Okay, this is how the Hammer cytometer look like. You have 25 square. Yeah, in 25 square here, and in this 25 you have another 25. All right, so you can see this is the grid line here. Okay, then you put your sample in. Okay, and then you follow this formula. For instance, the Hammer cytometer depth is 0.1 mm. So the 25 large square represent an area of 1 square mm. So as you only counting 5 squares, you don't have to count the 25. You only get the rough number. So you counted the sperm. For example, you count the sperm cell in your sample. That's set out of 0.2 microliter, which is 0.1 over 5, which is 0.02. Yeah, because the depth is 0.1. So multiply your count in 5 square by 50,000 in order to determine how many sperm would have been in 1 ml. Because 1 ml is equivalent to 1,000 microliters, right?
Yes.
Okay, you divided them by this one, 0.02, so you get the 5,000. Sorry, 50,000. What we call factors. Okay, then what you do now is the equation that follow would be used to convert the counts in 5 square to the concentrations in 1 ml. So the concentrations of sperm in 1 ml equivalent to the dilution factors time the count in 5 square time 0.05 10 to the power of 6. This one is this one. Yeah. So you know the dilution factors. You time the count in 5 squares time this one. Well, this one is 6. Right? So it's very easy. If you want to know more about how a Hammer cytometer can be used, then you can go to YouTube and have a look on that. Okay, Hammer cytometer counting. Or you may use the electronic counting. This is the easiest and less laborious. You don't have to do anything. You just dilute your sample and then you just put it in the vials into the cell counter and they directly give you the reading. This is the less laborious and easiest, the fastest way. Okay, by using electronic counting. Of course, the cost is much higher because you need to buy the machine. Okay, or you can use the growth curve. But growth curves, this is very time consuming and laborious. Okay, growth curves will increase the total cell number over time. So it's a good measure for a biological response that is widely defined and influenced by many different factors. Okay, because the growth factor curve can help you to differentiate between different effects. For example, changing the attachment, shortening or lengthening the lag phase, the changing of the plating efficiency, the dead rate, and also the plate tube. Right, this is the advantage, but it is very laborious and very much time consuming. Okay, this is the advantages of the growth curve. Okay, so this is the standard growth curve of the normal cell line. Okay, for example, you know they can tell you the doubling time, the lag time, the saturation density, and also the death phase. This is, for example, this is the normal growth curve, yeah, over the time and over the concentrations. Okay, so as I said just now, when you reseed your cell, they will undergo the lag phase. Lag phase is the cell are not replicating, but they are adapting to the new environment because you are providing them with the fresh media. So once they adapt to it, then they'll start to grow in the exponential way. Okay, and you can put feed them with the new batch of medium. Yeah. So until they are reaching stationary stage, almost reaching the stationary stage, this is a time for you to do subculture. Yeah. If you do not do subculture, what will happen is that the cell will go to the stationary stage, whereby at the stationary stage, the cell will not grow and will not be dividing. And if these keep going, then they are reaching the death phase. So all the cell will die and you are losing your cell. Okay, so this is the standard growth curve. Are you with me?
Yes, doctor.
Yes.
Okay. Right. What is a general growth curve shown to us? First is the lag phase. Lag phase means the time for the cell population to recover from subculturing, attachment, and spreading. Whereby the log phase means the cell number to increase exponentially, whereby this is the phase whereby cells are actively dividing. Okay, then they will be reaching a plateau phase whereby the culture becomes confluent and the growth rate slow or stop because there are medium exhaustions and also the limited space for the cell to grow. So, right. So, what is the plating efficiency? So, basically, it determines how a single cell can survive and form colony. It is a more sensitive measure of the cell response to its surrounding, and it also can be used as a method of choice for determining the nutritional requirements of the cell for testing and comparing the serum lots or the toxicity testing of the compounds. So this is a plating. How do we do plating efficiency? That we can express them in that percentage. For example, the colony form over the number of the colony the cell plated times 100%. Then you can have the plating efficiency. For instance, you plate 5 cells. Yeah, you plate 5 cells and the colony form is 50. So what is the plating efficiency?
$1,000.
1,000. Right? It's 1,000, right?
Yeah.
Yes, doctor.
Okay, so very easy. It's very straightforward actually. So, right now, how do we know we need to replace the medium? Okay, sometimes you have no idea how, when you need to replace the medium. First, you look at the drop in the pH. Okay, usually the drop in the pH is the color change because the phenol red is pinkish color, right?
Yes.
Okay, so when the change from pinkish to orange color, that means the pH already dropped. So that is also one of the indicator for you to do medium replacement. Okay. Or maybe you can check with the pH meter. Now you can get some of the samples and then you check on the pH. Use the pH meter and check the pH on the medium. From that is a direct way of doing it. Okay. So second method is the cell concentration. You can allocate a bit of this sample and then you examine under the microscope and look at the cell concentration. If the cell is concentrated and reaching confluence, that's also an indicator for us to do plasmid. Okay. Another one is the cell type, because you have fast growing cell and slow growing cell. Okay, depend on the cell characteristic. So if you have the fast growing cell, that means the replacement of the media is much faster compared to the slow growing cell. And another one is the morphological deteriorations. You can look at the morphological. Some of the cell, they look fine. Some of the cell, when you look under microscope, then the morphological change because of this maybe medium exhaustion or maybe because of the stress. So if you look at there's a morphological change or deterioration that you need to change your medium. So this is a 4 indicators for us to do medium replacement. Okay. So as I said just now, pH, most of the cells they grow at the pH at 7 to 7, pH 7 to pH 6.5, and they start to lose the viability between 6.5 to 6. Okay, so you need to check your pH of the medium so that your cell will grow in a conducive environment. Another one is the cell concentration. High concentration of cell will exhaust the medium faster. So this is a factor usually evidence of the rate of the change of pH, but of course not necessary. Okay, so you need to check, keep checking your cell, get the sample, assess them under the microscope to look for the evidence. Okay, and cell types also. The normal cell usually will stop dividing at a high cell density due to the cell crowding or growth factor depletion. The transformed cell and continuous cell lines and some embryonic stem cells, however, they deteriorate much faster at rate density unless the medium is changed daily or they are subcultured. Okay, especially these are fast dividing cells. Yeah. Another one is the morphological deterioration that must be anticipated by regular examination and familiarity with the cell line. So if the deterioration is allowed to progress too far, then the cell will not, it will be irreversible. That means the cell will, you will lose dispatch of the cell because they are going for the death fast. Okay, so by now you should know when the medium should be replaced. Okay, by looking at the parameters, 4 different parameters here. So far, okay?
Yeah, doctor.
Am I going too fast?
Yeah, doctor.
Okay, yeah. And cloning. So for this part, I will leave it to the next session. Okay. So after the next session, we'll talk about cleaning, the cloning, and how to isolate the cell line, and also how to choose, how to conduct cell line selection and characterization. Then after that, that's will be done with this 7 week of the lecture. Then we'll go for the